Hi everyone. Unfortunately, I'm having some issues printing at my house, so I'm just going to do what basically is going to be a walkthrough of the practice problems, and hopefully the voiceover and sort of talking through this can help you study if you're not able to make the review session, or if you just need a little bit of extra stuff to study while you're at home. Um, so let's start off with problem one here. This is on UART, and specifically the UART on the LPC 1768. So part A here is about the error ratio that we can have if we're doing UART on this board. And we sort of talked about this, that ideally we'd want something that is about 2.5%, sort of just back of the envelope, because that means that in total we'd have a 5% error, and that should mean that we don't end up missing any characters no matter where we end up starting in the stream. So here we're looking at the error, which is the actual baud rate, so what we achieve whenever we do this calculation, minus the expected baud rate, what we were trying to get to over the expected baud rate, or the projected, the target baud rate here. I think is what we use this year. So here we're trying to figure out what is the highest baud rate, the maximum baud rate that we can use in order to still end up within 5% error rate. In this case, we're using 5% instead of 2.5%. So maybe your company tells you that 5% is fine in this case. So here we're just solving for the error being 0.05 for 5%. We want the target baud rate of 9600 BPS as shown here. And we're solving for the actual baud rate. So what is the highest actual baud rate that we could come up with that still satisfies that 0.5 or 0.05 ratio? And so when we solve this, we multiply through by 9600, and then we add in 9600, and that gives us our actual baud rate of 10,080. For part B here, what we're looking for is we're trying to find the minimum and maximum baud rates that we can achieve on the LPC 1768. So this is sort of using the equation we have that is going to be used to calculate the baud rate. What are the sort of minimum and maximum parameters that we could put into this equation? So here we have the equation here, which is baud rate is equal to the P clock. Remember, that's the peripheral clock, so we can select that with P clock select. So it's not guaranteed to be 100 megahertz, so that would be the highest value we could give. We have 16 times 256 times DLM plus DLL. So in total, this is the sort of full 16 bits that we can put into the divisor for the baud rate calculator. And then we have our fractional value that we can use here. So I'm going to go ahead and click into the manual here so we can look at some of these tables. And you can see the sort of basic configuration here talks about how to set the baud rate. So we can actually find the tables that we need from here. And so I can see that DLL and DLM are both 0 to 7 bits in this particular register. And again, we're just kind of matching the symbols here to what we're looking for. So this is 8 bits total for each of these. And I would know that 2 to the 8th minus 1, or we can calculate that, is going to be 255. So 255 is the largest value that I can put into one of these and make it work. And so that's going to be, if I sort of max out my divisor, that's going to lead to a smaller baud rate. So if I sort of max out these values to 255, that's what I can fit into each of those. That's going to be my maximum value on the divisor. So that's what I want to use to sort of calculate this as the highest possible maximum value. I can also look at the values, if I go back here, that I can put into the fractional divisor register. So this is the div add val and mul val values, and I can get the sort of minimum and maximum from this table here. So these are in FR, that's the sort of biggest and smallest values that we can get by doing 14 divided by 15. If we only have those 4 bits for div add val and mul val, this is the largest and smallest fractions that we can get for this FR value that we have here, this fractional divisor. And so if I want to get the maximum value, that's going to be 1.933. If I want the minimum value, that's going to be 1. And so that's what I'm going to do here, is basically just plug in the maximums to find the minimum baud rate. I also need to know the minimum and maximum clock speed. And so if we look up real fast, PCLK cell 0. We can find p clock select in the manual here. We can see that our options for p clock are always going to be clock divided by 4, clock divided by 2, and clock divided by 8. And hopefully you're familiar with those at this point. So the minimum clock we can get for p clock is going to be clock divided by 8. That's going to be our thing we're dividing. So we want that to be as small as possible for finding the minimum baud rate, and we want it to be as large as possible for finding the maximum baud rate. And so here we're going to use p clock max in the maximum baud rate calculation, and p clock min is baud rate or clock divided by 8. Clock is always going to be, so c clock here is always going to be 100 megahertz. And that means that when we divide that by 8, we get 12.5 times 10 to the 6 hertz, or 12.5 megahertz as our minimum baud rate clock. And so that we plug all these, the sort of minimum clock divided by the maximum DLL, DLM in fraction, and that gives us that 6 BPS that we can have this our smallest baud rate possible. So 6 bits per second, pretty slow. For the max, again, we're going to plug in the p clock max there. And then we're trying to find the smallest possible value that I can give for DLL and DLM. And so here I can just not add anything in. I need to have at least 1 here so we don't divide by 0. So DLL, because we're adding that, has to be 1. But DLM can be 0. That gets rid of the 256 times DLM. And then 16 times 1 is going to leave us with 16. And our smallest fractional divisor that we can have is 1. So we end up with 100 megahertz divided by 16, which is going to give us 6,250,000 bits per second. So that's our maximum baud rate. So this is really just knowing the limits of these different data registers on the LPC 1768 and being able to plug them into the baud rate equation. So next up, part C. So given a target baud rate of 1200 BPS, what value should be used for DL, FR, div-adval, and mol-val? So here we are again going to look at the UART tables. And if we scroll down here, we should eventually find that that flow chart that we use to calculate these values. Or you can look this up in the notes. But it is in the manual here, page 314. So we see we basically choose p clock and baud rate, and then we calculate DLS using this equation. And so that's exactly what I'm going to do here is we can choose a p clock. So we don't have that given to us. We can just choose whatever value we want to use there. I forget what I used in this problem, and I don't actually have it written down. So we'll just assume that it is 100 megahertz because I didn't list anything otherwise. So we're going to do 100 megahertz divided by 16 times DLS. And that's going to give us a DLS of 5,208.33 repeating. This is not an integer. So what we can do here is we can plug this back into the baud rate equation and see how close we get to the baud rate that we want of 1200 BPS. If that's within 2.5% error, we can stop right there. So we can basically combine this equation with this equation and check to see is this the amount of error that we're okay with. If not, then we have to try to estimate something further. So that's here we do is DLS an integer. If it's not, then we're going to set FRS to 1.5. We're going to use the DLS equation given here in the manual to estimate what our new value for FRS or what our new value for DLS should be. So that's what we're doing here is we do p clock over 16 times baud rate times 1.5. That 1.5 is the FRS equals 1.5 that we're estimating with. And that gives us 3472.22 repeating. And so this is pretty close to an integer at this point. We can maybe assume that FRS of 1.5 is fine, but let's just calculate through to see if that's the closest thing we have. So we repeat that equation, or we use this equation now for FRS. We plug in the DLS that we got, but we round it to an integer because at the end of the day, DL is going to be an integer value. And so we do p clock divided by 16 times BR, which is 1200, times 3472, rounded this number to an integer. and that comes out to approximately 1.5. So it seems like 1.5 for FRest is as close as we're going to get. It's between these parameters here of 1.1 and 1.933, and so that means we can calculate div add val and mol val given our table, and we can slide up and find what that, or slide down and find what that is. So we look up 1.5 in this table. FR of 1.5 means div add val is 1, mol val is 2. And then DLM equals the top 8 bits of DLS. DLL equals the bottom 8 bits of DLS. So here we're essentially just converting this 3472 into hex, and so we would end up with D being the top 8 bits, that's what goes into DLM, and the 90 being the bottom 8 bits, that's what goes into DLS, or DLL. So that's really it for this problem. It's just sort of following this flow chart to a T, pulling the equation straight out of here. When it says int, that means to round to an integer, and that's really all you should have to do for a baud rate problem. So that's it. A little bit long maybe, but hopefully the rest will be a little shorter.